What if I told you that everything you see, the stars, the galaxies, even time itself, might not be free at all, but trapped inside a black hole so massive, so mysterious, that it contains our entire universe? Sounds like science fiction, right? Well, some scientists believe it could be reality. And if they're right, the Big Bang wasn't the beginning of everything. It was just the other side of a cosmic collapse. So, are we really living inside a black hole? Let's find out. What if everything you've ever known, from galaxies to stars, from time itself to the fabric of space, is not truly free, but trapped? Imagine for a moment that our universe, the vast expanse stretching billions of light years, is not open at all, but actually the inside of a black hole. This idea may sound like pure science fiction, but believe it or not, some scientists have taken this hypothesis seriously. And if it's true, our entire reality could be far stranger than we ever imagined. Throughout history, humanity has looked at the night sky and wondered where we come from and where we are going. Questions about origins, about meaning, and about our place in the cosmos are timeless. The thought that our entire universe might itself be inside a cosmic prison adds a whole new layer to that mystery. Could the universe we live in really be hiding behind the same physics that governs the most terrifying objects in space? When people hear the term black hole, they often picture a dark, devouring monster in space, consuming anything that gets too close. That's not entirely wrong, but the concept goes much deeper. The question we're exploring today is not about falling into a black hole. It's about whether we are already inside one. Think about that. Not outside, not observing from afar, but living inside its very core. This is not a wild fantasy pulled from a sci-fi novel. In fact, the idea finds roots in real physics, in equations that stem from Einstein's general theory of relativity. The strange thing about these equations is that, when pushed to their limits, they sometimes suggest things so bizarre that they challenge our sense of reality. One of those strange possibilities is that black holes don't just destroy, they might also create. If black holes can create, then what do they create? Could they give birth to entire new universes? Some scientists suggest that what we see as a Big Bang might in fact be the other side of a black hole. In that case, our universe might not only be inside a black hole, it might have been born from one. That possibility is not only mind-bending, it's also deeply unsettling. Now here's where the curiosity really grows. Black holes are defined by their extreme gravity, pulling everything inward. If our universe is a black hole, then why does it seem to be expanding outward? That's one of the paradoxes we'll explore today. The answers may lie in how time and space behave in ways that defy our intuition. So as you watch, ask yourself, what if every galaxy you see, every star shining in the night, is just part of a larger construct trapped in a black hole's invisible grasp? And if that's true, what lies beyond it? Another universe? Or something else entirely? By the end of this journey, you might look at the cosmos with completely new eyes. To answer these questions, we need to start with the basics. What exactly is a black hole, and how do we know they exist? Before we can even begin to consider living inside one, we have to understand what they are from the outside. That foundation is crucial if we want to even glimpse the truth behind this bold idea. Prepare yourself, because the deeper we go, the stranger things will get. Every answer will open new questions, and every explanation will challenge your perception of reality. That's the beauty of exploring mysteries this big. They don't just feed curiosity, they transform it into wonder. So let's begin at the beginning. Let's look at what a black hole actually is, and why it's so important to understanding whether we might be living inside one right now. What is a black hole? At its core, a black hole is a region of space where gravity is so powerful that nothing, not even light, can escape. Imagine compressing a massive star larger than our sun down to an unimaginably small point. Once it collapses, the density becomes infinite and the gravitational pull becomes absolute. That tiny point of infinite density is called a singularity. Surrounding it is an invisible boundary known as the event horizon. The event horizon is not a solid surface, it's a limit. Once something crosses it, there is no way back. Not light, not matter, not even information can return. This is why black holes appear perfectly black. They trap everything. They are, in essence, one-way doors in the universe where things can enter but never leave. The idea alone sparks fear and fascination in equal measure. There are different types of black holes. Some are born from the death of massive stars, when their fuel runs out and gravity causes them to collapse inward. These are called stellar mass black holes. Then there are the giants, supermassive black holes, which sit at the centers of galaxies, millions or even billions of times more massive than our sun. The Milky Way itself hides such a monster at its heart, Sagittarius A. Scientists didn't always believe black holes were real. For decades, they existed only in theory, a bizarre prediction of Einstein's equations. But evidence grew, especially when astronomers observed stars orbiting invisible objects with incredible speed. Then came the first actual images of black holes, captured by the Event Horizon Telescope. Suddenly, something that once seemed like abstract math became visually real. Understanding black holes is critical for more than just astronomy. They challenge the very laws of physics, forcing us to confront what happens at extremes where our current knowledge breaks down. At their core, they merge gravity, time, and space into something that stretches human understanding to its limits. Here's the twist. As terrifying as they seem, black holes may not just be cosmic destroyers. They might also be cosmic creators. If the mathematics holds true, every black hole could potentially open into a brand new universe. That raises the question, what if our own universe is just one such creation? Think of it like this. To an outside observer, a black hole is a region that only consumes. But from the inside, from another perspective, it might look like an expanding universe just like ours. That duality is at the heart of the hypothesis we're exploring. Could we, without even knowing it, be residents of a black hole's hidden interior? This idea ties back directly to Einstein's general relativity. The same equations that predict black holes also allow for the expansion of entire universes. Could these two ideas be one and the same? That's the leap that makes the theory both mind-bending and surprisingly plausible. So while most people think of black holes as cosmic monsters, swallowing light and matter, today we have to rethink that picture. What if instead of endings, black holes are beginnings? And what if our universe itself is proof of that? To find out, we need to look deeper into how horizons work, both in black holes and in our universe, because hidden in that comparison might be the first real clue that we are living inside a black hole ourselves. The concept of the event. Horizon. To truly understand why scientists even consider the possibility that we're living inside a black hole, we must first grasp the concept of the event horizon. Picture it as a boundary, an invisible surface surrounding the black hole. Cross it, and you're lost forever. Light, matter, information, everything is trapped beyond this threshold. It's not a physical wall, but rather the ultimate point of no return. In simpler terms, imagine standing at the edge of a cliff so steep and so deep that even throwing a beam of light won't help. It never comes back. That's how the event horizon behaves. From the outside, you can only see objects approach the horizon, but never cross it. From the inside, escape is impossible. This unique property makes black holes unlike anything else in the universe. Now here's the fascinating part. Our universe also has something like an event horizon. We call it the cosmic horizon. It's the maximum distance light could have traveled since the Big Bang, about 13.8 billion years ago. Beyond this horizon, we cannot see or receive any information because light hasn't had enough time to reach us yet. This similarity between a black hole's horizon and the universe's horizon raises eyebrows. Both represent boundaries of knowledge, limits to what can be observed. Inside the cosmic horizon, we see galaxies, stars, and planets. Beyond it, silence. Not because nothing exists there, but because the universe isn't old enough to let us see that far. Here's where the analogy grows stronger. In black holes, the event horizon defines the size of the black hole. In our universe, the cosmic horizon defines the size of what we can observe. Two different phenomena, yet eerily similar in function. Could this parallel be more than coincidence? The event horizon also ties deeply into how time and space bend near extreme gravity. Observers outside see things slow down near the horizon, almost frozen. Meanwhile, for an object falling in, time seems to pass normally. This paradox is crucial because it suggests perspective matters greatly when dealing with horizons. Now imagine flipping that perspective. If we're inside a black hole, our experience of expansion could simply be the result of being on the other side of an event horizon. To us, the universe grows outward. To an outsider, it could look like everything has been trapped forever. Same reality, two views. So, as we compare these two horizons, the black holes and the universes, we begin to see hints of a possible connection. Could it be that our cosmic horizon is not just a boundary of time, but the event horizon of a massive black hole? The deeper we look into this comparison, the more unsettling it becomes. Horizons aren't just barriers, they are clues. And following them leads us to wonder if the very size of the universe matches what we'd expect from a black hole's event horizon. That's our next step, the mass and size of the universe. Here's a fascinating exercise often given to graduate students in physics. Take the estimated mass of the observable universe and calculate how large a black hole would be if all that mass were packed into one. The result is astonishing. The black hole's event horizon would be almost the exact size of our observable universe. Coincidence? Or a hidden truth? To put this into perspective, the observable universe contains around 1,053 kilograms of mass. That's a number so large it's nearly impossible to comprehend. If you compress that much matter into a single point, you create a black hole with a radius of about 13.8 billion light years, the very distance to our cosmic horizon. Think about that for a moment. If you ask, how big would a black hole containing our universe's mass be? The answer is, exactly as big as our universe itself. That's not just a rough match. It's a striking alignment between theory and observation. Of course, the skeptics might say this is merely a mathematical trick, an accidental overlap of numbers. But science often advances when coincidences turn out to be hidden laws. Could it be that this is more than chance? Could it be the universe whispering the truth of its own nature? Another point to consider. The more massive a black hole, the larger its event horizon. Double the mass, double the size. It's a linear relationship. When we run this math with the universe's mass, we get a result that doesn't just make sense. It mirrors reality. So, if the size of our universe matches the size of a black hole with the same mass, the line between the two concepts blurs. Are we looking at a universe, or are we trapped inside a cosmic black hole, unable to see beyond its horizon? But this thought experiment raises even deeper questions. If our universe is a black hole, where did it come from? Was it born from another collapsing star in a larger reality? If so, then the Big Bang might not have been the beginning of everything, just the beginning of our bubble. This view paints the universe not as infinite, but as one of many possible creations. Each black hole could be a seed for a new universe, growing on the other side of an event horizon. If that's true, then our own existence may be part of a cycle far grander than we can imagine. Still, before we leap into speculation, we must pause. Science requires more than curious coincidences. We need evidence, and we need to test these ideas. Yet even now, the parallels between our universe's size and a black hole's cannot be ignored. And this leads us to the big question. Is this similarity just coincidence, or actual evidence that we live inside a black hole? The answer may lie in how we interpret density and cosmic structure, the next piece of the puzzle. Coincidence or evidence? When scientists noticed that the average density of matter in the universe matched what you'd expect inside a black hole of the same size, the question naturally arose, is this just coincidence, or is it actual evidence? Physics is full of coincidences that later revealed deep truths. Could this be one of them? On the surface, it seems almost too neat. The universe's density, mass, and radius line up almost perfectly with black hole equations. If it were slightly off, we might dismiss it as a quirk of math. But the match is so precise that it begs for explanation. After all, why should our universe's numbers look like those of a black hole at all? Skeptics argue that coincidences are not proofs. They warn that just because two sets of numbers align doesn't mean they describe the same reality. Yet, in science, patterns often lead to revolutions. Think of Kepler noticing planetary orbits or Einstein seeing patterns in gravity and acceleration. What looks like chance may instead be a cosmic clue. The intriguing part is that this alignment doesn't just happen once. Both the universe's density and its expansion behavior show echoes of black hole physics. In fact, some cosmologists suggest that the laws inside a black hole might look indistinguishable from what we already observe in our expanding universe. Now imagine what that means. The universe wouldn't just be like a black hole, it would be one from the perspective of a higher reality. From our side, we see galaxies drifting apart, space expanding, and time moving forward. From the outside, it could all appear frozen at an event horizon. If this alignment is real evidence, it changes how we view the Big Bang. Instead of an explosion from nothing, it becomes the birth of a universe inside the collapse of something else. Suddenly, our cosmic beginning doesn't look like the start of everything, but rather the continuation of a larger chain. Still, we must tread carefully. Science thrives on caution. Many researchers consider this an elegant speculation, but not yet a confirmed fact. After all, we can't step outside our universe to test whether it truly resembles a black hole. That limitation keeps the idea in the realm of theory. Yet, even if unproven, the idea forces us to ask bigger questions. What counts as evidence when we're dealing with something as large as the universe itself? If the math matches perfectly, is that not itself a kind of proof? Or do we demand more? This is where philosophy and physics meet. A coincidence may be dismissed, but a pattern may reveal truth. Deciding which one we're looking at will shape the future of cosmology. For now, the mystery remains. Are we seeing numbers that tease us? Or numbers that reveal our prison? To explore this puzzle further, we need to turn to the most radical possibility, that black holes are not just endings, but beginnings. That what we call death in one universe is birth in another, which brings us to the astonishing theory of new universes within black holes. The idea of new universes. Inside black holes. Einstein's general theory of relativity does more than describe black holes. It suggests that entire new regions of space-time might open up beyond them. Instead of being a dead end, the inside of a black hole could blossom into a completely new universe. In this view, black holes are not just destroyers, but creators. The idea goes like this. When a massive star collapses into a singularity, it creates an event horizon around it. From our perspective, everything falls in and vanishes. But on the other side of that singularity, the equations allow for space-time to continue unfolding. That continuation could look to those inside like a new expanding universe. In fact, this resembles the story of our own universe. The Big Bang looks like a singularity from which space, time, and matter suddenly emerged. What if that singularity wasn't the beginning of everything, but rather the inside of a black hole formed in another universe? Suddenly, the birth of our cosmos gains an unexpected parent. This theory also elegantly explains why universes expand. Inside a black hole, space would naturally stretch outward from the singularity, appearing to its inhabitants as cosmic expansion. What we see as galaxies drifting apart could simply be the internal view of a black hole's geometry. Now here's where things get truly mind-bending. If every black hole creates a new universe on the inside, then universes could exist in an endless chain. Each universe spawns new universes within its black holes, creating a cosmic family tree stretching infinitely. Our universe could be just one branch among countless others. This raises fascinating implications for physics itself. What if the laws of each universe are inherited from the black hole that birthed them? That would mean the properties of our cosmos, its gravity, its particles, even the strength of its forces, might be shaped by the collapse that created us. Some scientists call this cosmological natural selection. In this view, universes that produce more black holes would also produce more offspring universes. Over time, universes evolve just like living organisms, favoring conditions that make black holes, and therefore new universes, more likely. Still, as exciting as it sounds, the idea is difficult to test. We cannot peek inside a black hole to confirm whether it leads to another universe. nor can we observe our universe from the outside to confirm whether it's inside one. These limitations keep the theory in the speculative realm. Yet the concept has enormous philosophical power. Instead of seeing black holes as cosmic graves, we can view them as cosmic wombs. They may not mark the end of creation, but the birth of endless new realities. And if that's true, then perhaps our universe is not unique. It's simply one child in a vast multiverse, born inside a black hole of another world. The question then is not whether we are special, but how many universes like ours might exist. Time inside a black hole. One of the strangest effects of black holes isn't their ability to swallow matter, it's how they distort time itself. According to Einstein's relativity, the stronger the gravity, the slower time flows. Near a black hole, gravity is so intense that time practically grinds to a halt compared to regions far away. This effect is called time dilation. From the perspective of an outside observer, anything falling toward a black hole appears to slow down infinitely as it nears the event horizon. The object never seems to cross it, it just fades and stretches. Yet from the perspective of the falling object, time feels completely normal. This paradox shows how relative and slippery time becomes under extreme gravity. Now, imagine living inside a black hole. To us, everything would appear natural. Seconds ticking, galaxies forming, stars living and dying. But to someone outside, if such an observer could exist, our entire universe might look frozen in time, trapped at the edge of an event horizon. Our sense of normalcy might itself be an illusion shaped by perspective. This is where the idea of the universe as a black hole gains depth. The expansion of space that we observe could be the natural unfolding of time inside a black hole. The slowing, the stretching, the bending, all could simply be the manifestation of extreme relativity on a cosmic scale. In fact, scientists often point out that the equations of relativity don't forbid such scenarios. Time inside a black hole can behave in ways that defy ordinary understanding. To the inhabitants, it may look like billions of years of cosmic history. To the outside, it could be just a single instant. This duality challenges our very concept of time. We think of it as absolute, a steady flow from past to present to future. But black holes reveal that time is not universal. It is relative to gravity. And if our universe is inside a black hole, then our entire experience of time may be just one perspective among many. What makes this even more curious is that time dilation is not just theory, it's measurable. GPS satellites orbiting Earth must account for tiny differences in time caused by weaker gravity compared to the surface. If relativity holds true here, why wouldn't it hold true on the scale of universes? This leads to an unsettling possibility. What if our sense of the universe's age, 13.8 billion years, is only valid from inside? To an outside perspective, our universe might be infinitely younger or even timeless. Time itself could be a local phenomenon, confined to the bubble we call reality. The idea of time being relative already bends our minds. But inside a black hole, relativity reaches extremes. If our universe truly exists within one, then time as we know it is not universal truth, it is a local illusion. And that makes us ask, what does that say about our beginning, the Big Bang itself? The Big Bang and its link to stellar collapse. For over a century, scientists have believed that the universe began with the Big Bang, a sudden expansion of space and time from a single point of unimaginable density. But if our universe is inside a black hole, then perhaps the Big Bang wasn't the absolute beginning. Maybe it was the continuation of something else, the collapse of a massive star in another universe. Imagine this. In a larger parent universe, a star many times bigger than our sun collapses under its own weight, creating a black hole. From the perspective of that universe, the star dies, vanishing into darkness. But from our perspective, inside the black hole, a new universe explodes into existence. What looks like death in one reality is birth in another. This view reframes the Big Bang. Instead of appearing out of nothing, our universe could have been born inside the singularity of a massive collapse. That collapse provided the energy, density, and initial conditions we interpret as the beginning of everything. In truth, it may have just been the beginning of our branch of reality. Such a model also explains why the Big Bang didn't explode into pre-existing space. It created space itself. Inside a black hole, space unfolds naturally. Expansion isn't just an effect, it's built into the geometry. To us, it looks like galaxies racing apart. To the outside, it might just be the stretching interior of a black hole. This connection between collapse and creation also fits the cyclical patterns we see in nature. Stars die and create new elements. Black holes consume, but perhaps they also give birth. Could universes follow the same rhythm? If so, ours may be one in an endless cycle of birth and death. Some scientists argue this idea helps explain why our universe appears so finely tuned. If universes are born from collapsing stars, then each new universe might inherit physical laws from its parent. Over countless generations, only those universes capable of forming stars and black holes survive. The cycle ensures self-replication, like a cosmic form of evolution. Still, the theory raises difficult questions. If our universe came from a collapse, what did that parent universe look like? Did it have similar laws of physics? Or are the differences so vast that we'd never recognize them? Each black hole might be a doorway to a universe with entirely new rules. The Big Bang, in this light, becomes less mysterious but more profound. Instead of a singular miracle, it is a natural consequence of collapse. It is not the creation of something from nothing, but the transformation of one reality into another. If this is true, then the death of stars may echo across universes. Each collapse in one world becomes the seed of another, and our Big Bang may just be one among infinite beginnings. This leads us to an even more puzzling mystery. Is there evidence inside our universe that hints at such origins? Could cosmic patterns, like rotation, be the fingerprints of our black hole parentage? The enigma of cosmic rotation. When we think of the universe, we often imagine it as vast, chaotic, and random. Galaxies form, stars ignite, planets spin, each seemingly independent. But recent observations suggest something unexpected. The universe itself might have a preferred direction of rotation. If true, this discovery could reshape our entire understanding of cosmic origins. Astronomers studied hundreds of spiral galaxies, carefully examining their rotation from different parts of the sky. If the universe were perfectly random, we'd expect half of the galaxies to spin clockwise and the other half counterclockwise. But the data revealed something strange. About 2/3 of them rotate in the same direction. That's not balance. That's a hint of order. Why does this matter? Because in physics, large-scale order usually points to a deeper cause. If galaxies across billions of light years all share a similar orientation, it suggests the universe itself may have inherited angular momentum. And if the universe has a net spin, that raises an incredible possibility. It might be behaving exactly like the interior of a black hole. Normally, we assume galaxies spin because of local conditions. Gas clouds collapse, conservation of momentum speeds them up, and the result is a rotating star system or galaxy. But those rotations should be independent, not coordinated across the cosmos. Random turbulence should cancel everything out. Yet, the evidence hints at a pattern. Critics argue the dataset is too small, just a few hundred galaxies in a universe of billions. More research is needed. Still, even a faint suggestion of net rotation is fascinating. It challenges our assumption that the universe has no preferred direction, no cosmic axis. If such an axis exists, it may point to something fundamental about our origins. The idea of a spinning universe ties directly into black holes. When matter falls into a black hole, it rarely does so evenly. Instead, it swirls like water down a drain. That spin, that angular momentum doesn't disappear. It becomes part of the black hole itself. If our universe shows signs of rotation, could it be the legacy of the black hole that birthed us? This enigma forces us to reconsider randomness. Perhaps the universe's rotation is not coincidence, but inheritance. Just as children carry traits from their parents, universes may carry traits from the black holes that spawned them. Spin could be the fingerprint left behind by our cosmic origin. But before we leap to conclusions, we must remember, science thrives on skepticism. A larger sample of galaxies could confirm or completely overturn this hint of cosmic rotation. Until then, the mystery remains suspended between possibility and illusion. Still, even uncertainty sparks imagination. If the universe truly rotates, then we might already be looking at evidence that we're living inside a black hole. The spin we observe could be the hidden echo of our parent universe's collapse. And that leads us naturally into the next idea: angular momentum. To understand cosmic rotation, we must first understand the universal principle that governs spin at every scale. The role of angular momentum. Angular momentum is one of the most fundamental principles in physics. It's the rule that explains why planets spin, why galaxies rotate, and why a figure skater spins faster when pulling in their arms. In essence, it's the property of motion that resists change. Once something has angular momentum, it keeps it unless acted upon by an outside force. This principle is not confined to small scales. It governs everything from atoms to entire galaxies. For example, when a massive gas cloud in space begins to collapse under gravity, even the tiniest initial motion becomes magnified. As the cloud shrinks, it spins faster, just like the skater pulling in her arms. Eventually, this rotation gives birth to stars, planets, and even galaxies. Now imagine scaling this idea up to the level of universes. If a black hole is spinning, and many do, then any universe forming inside it might inherit that spin. Angular momentum doesn't vanish. It carries forward, shaping the newborn universe. Could our universe's possible rotation be nothing more than cosmic inheritance? This idea elegantly ties back to the observed galaxy rotations. If they're not truly random, if they reveal a preferred spin direction, then angular momentum conservation could be the key. Our universe may simply be reflecting the momentum of the black hole it was born from. Of course, the conservation of angular momentum is not just theory, it's tested everywhere. From the orbits of satellites to the spin of Earth itself, we see it in action daily. That reliability makes it a strong candidate for explaining large-scale cosmic behavior as well. The real question becomes, how does angular momentum work across the boundary of universes? If every black hole leads to a new universe, then each collapse may pass down not only mass but also spin. The result? A cosmic family tree, where universes inherit physical traits from their predecessors. This perspective radically changes how we see the Big Bang. Instead of a random explosion from nowhere, it becomes a continuation of motion. The expansion we observe is not arbitrary. It's shaped by the conservation of angular momentum, a universal law that spans realities. Still, this hypothesis raises challenges. Can we measure the universe's net rotation accurately enough to prove it? Can we ever detect the signature of our parent black hole? These questions remain unanswered, but they show how deep the implications run. If angular momentum really is conserved across universes, then our cosmic story is not isolated. We are part of a chain of inheritances stretching back through countless collapses. Spin becomes the thread that connects one universe to another. And if that's true, then every galaxy we see spinning in the night sky is more than a structure of stars. It's evidence of a deeper truth. That motion itself is eternal, carried forward through the endless cycle of universes. The conservation of motion and everyday examples. Sometimes the most complex cosmic ideas can be understood by looking at simple, everyday experiences. Take, for instance, the figure skater. When she spins with arms extended, her rotation is slow. As she pulls her arms closer to her body, she spins faster. Why? Because angular momentum must be conserved. The same amount of spin is compressed into a smaller space. This same principle applies to collapsing gas clouds in space. Even the tiniest initial rotation becomes amplified as the cloud contracts under gravity. What begins as a slow, almost imperceptible spin grows faster and faster until it gives birth to stars and planetary systems. In this way, the same principle that governs a skater also shapes entire galaxies. The conservation of angular momentum is so universal that it's nearly impossible to escape. Planets spin, moons rotate, galaxies swirl, all because motion cannot simply vanish. It must be preserved and transformed. This is why it's so rare to find anything in the universe that isn't rotating in some way. But here's the fascinating twist. If every star, planet, and galaxy inherits rotation from collapsing matter, what does that say about the universe as a whole? Could the entire cosmos itself be rotating because it inherited spin from something greater, perhaps the black hole that birthed it? The everyday examples make this idea easier to grasp. Think of draining water spiraling into a sink. That swirl isn't caused by the water itself. It's the natural result of conservation of momentum. Similarly, galaxies spinning in the same direction might not be random chance. They could be echoes of a deeper, inherited motion. Even turbulence in gas clouds, chaotic as it may seem, still follows the same principle. No cloud is perfectly still. Tiny motions always exist, and when compressed, they magnify into full-blown rotations. This inevitability of motion suggests that randomness rarely erases spin. It almost always produces it. Now scale that idea up again. If galaxies, stars, and planets cannot escape spin, why would universes be any different? If a universe is born from a black hole, then its inherited angular momentum would dictate cosmic behavior on the grandest scale. This realization makes conservation of momentum one of the strongest pieces of evidence for the universe inside a black hole hypothesis. It shows that spin is not optional, it's inevitable. And if it's inevitable on small scales, it might be inevitable on cosmic ones too. Still, we must tread carefully. While everyday examples illuminate the principle, they don't prove the universe itself rotates. They simply make the idea more relatable. But they do raise the tantalizing possibility that our cosmic behavior is not random. It is inherited. This brings us to an important turning point. Even with all these elegant connections, we must confront the limits of this theory. Because while it's exciting, it also carries gaps and uncertainties that cannot be ignored. The limitations of the theory. Every bold hypothesis must face the test of skepticism. And the idea that our universe exists inside a black hole is no exception. While intriguing, it comes with serious challenges that make many scientists cautious. First and foremost, we cannot observe our universe from the outside. Without that perspective, proving we're inside anything is nearly impossible. Another limitation lies in the mathematics itself. While Einstein's relativity allows for black holes to create new spacetimes, it doesn't guarantee they do. The equations are open to interpretation, and different solutions can describe very different realities. Some may allow for new universes, others may not. The math alone cannot decide. There's also the problem of testability. Good science relies on experiments and observations. But how do you run an experiment on the entire universe? Unlike galaxies or stars, the cosmos doesn't fit into a telescope in the same way. Our inability to gather direct evidence makes this theory speculative at best. Skeptics also point out that coincidences don't equal causation. Just because the universe's density and size align with black hole equations doesn't prove they're the same. It may simply be a numerical overlap with no deeper meaning. The history of science is filled with patterns that turned out to be coincidences. Furthermore, cosmology already has a strong framework: the Big Bang Theory and the Standard Model of Cosmology. These models explain expansion, cosmic background radiation, and galaxy formation, without requiring us to live inside a black hole. Adding the black hole hypothesis might be unnecessary if simpler explanations already fit. Another issue is the singularity problem. Black holes, as currently understood, contain singularities, points of infinite density. But infinities in physics usually mean our theories are incomplete, not that reality is infinite. Until we resolve this, basing a whole cosmological model on singularities is shaky. Quantum physics adds more complexity. General relativity explains gravity well, but it clashes with quantum mechanics at extreme scales. Without a theory of quantum gravity, we lack the tools to truly understand what happens at the core of a black hole, let alone whether it creates universes. Some also argue that rotation evidence is weak. The galaxy sample showing net spin was relatively small. With billions of galaxies out there, larger studies may show no overall pattern at all. Until then, rotation as proof remains tentative. So while the theory is mind-bending and beautiful, it remains speculative. Its limitations highlight the line between science and philosophy, between what we can know and what we can only imagine. And that's precisely why it fascinates us. The gaps in the theory don't kill curiosity, they ignite it. But to balance speculation with reality, we must also ask, what does mainstream science actually think of this idea? What mainstream science thinks about this idea? In the world of physics, radical ideas are not rare, but for a theory to gain acceptance, it must survive rigorous testing and peer review. So where does mainstream science stand on the idea that our universe might be inside a black hole? The answer is a cautious mix of fascination and skepticism. On one hand, many physicists admire the elegance of the hypothesis. It ties together general relativity, black hole physics, and cosmology in a way that sparks creativity. It also provides a possible explanation for the Big Bang's mysterious origin. If black holes give birth to universes, then our own existence might simply be part of a natural process. However, mainstream cosmology already has a robust model, the Lambda CDM model, which combines the Big Bang, cosmic expansion, dark matter, and dark energy. This framework explains most observations, from the cosmic microwave background to the structure of galaxies. Importantly, it doesn't require us to live inside a black hole. That doesn't mean scientists dismiss the idea outright. Some researchers explore it as a thought experiment, a way to push the boundaries of relativity and quantum mechanics. But they remain careful to separate speculation from evidence. After all, without measurable proof, the hypothesis is more philosophy than physics. Another issue is that black holes are difficult to study even within our own universe. We can observe their effects on nearby matter, but the interiors remain hidden. If we can't understand black holes here, how can we confidently claim to live inside one? The challenge is not just theoretical, it's observational. Still, the idea lingers in scientific discussions. That's because it addresses one of the biggest unanswered questions: what caused the Big Bang? Standard models describe how the universe expanded, but not why it began in the first place. The black hole hypothesis offers a possible answer, even if it's unproven. Scientists who are intrigued by the idea often stress that even if it's wrong, exploring it could lead to new discoveries. History shows that speculation sometimes paves the way for breakthroughs. What begins as too crazy may one day become mainstream once evidence catches up. But for now, most physicists remain cautious. They acknowledge the beauty of the hypothesis, but they stop short of calling it a serious contender. Without experiments or data, it's impossible to elevate it beyond theory. And yet, the very fact that serious scientists even consider the possibility shows how open the frontier of cosmology still is. We may not live inside a black hole, but asking the question pushes us to expand the limits of what we're willing to imagine. This tension between science and imagination leads naturally to a deeper issue. If the idea is true, what would it mean not just scientifically, but philosophically? The philosophical impact of the idea. Sometimes, the most powerful ideas are not about what they prove, but about how they change the way we think. The possibility that our universe is inside a black hole is not just a scientific question, it's a philosophical one. If true, it would reshape how we view existence, reality, and our place in the cosmos. First, it challenges our sense of beginnings. We often imagine the universe as the ultimate origin, the absolute starting point of everything. But if our universe was born inside another, then beginnings are illusions. Reality becomes a chain of births and deaths, where every end is a new beginning. It also challenges our sense of scale. We already feel small when we look at the stars, but what if our entire universe is just a bubble inside a larger reality? That would mean even the vastness of billions of galaxies is just one tiny pocket in an endless sea of universes. Philosophically, this idea touches on the question of meaning. If universes can be born and reborn endlessly, does that make our own existence less significant or more? Perhaps meaning doesn't come from being unique, but from being part of an infinite cycle of creation. It also opens the door to the multiverse idea. If every black hole spawns a universe, then reality is not singular but plural. We are one of many universes, each with its own laws, histories, and possibilities. This dissolves the notion of an absolute reality, replacing it with an infinite variety of realities. Some thinkers argue that this perspective is humbling. It strips away the idea that our universe is special. Others argue the opposite. Being part of such a grand cycle makes our existence even more profound. We are the living evidence of a process that transcends universes themselves. The hypothesis also blurs the line between science and philosophy. It shows how physics, when pushed to its limits, inevitably raises existential questions. Are we living in a black hole? Or are we imagining metaphors to describe what we cannot yet understand? In either case, the effect is the same. We are forced to confront the mystery of existence. What's fascinating is that this question has no easy answer. It may remain unsolved forever. But in raising it, we expand not just our scientific horizons, but also our philosophical ones. The universe becomes not only a place to measure, but a place to wonder. And in the end, perhaps that's the greatest impact of all. Even if we never prove the idea true, it forces us to see ourselves differently, not as detached observers of the cosmos, but as participants in its deepest mysteries. Which brings us to the final question. If this is true, what should we take away? How should we conclude a journey into one of the strangest possibilities ever imagined? Mysterious and provocative conclusion. So after this journey through horizons, densities, rotations, and philosophical reflections, where do we stand? Are we truly living inside a black hole, or is this just an elegant coincidence of mathematics and imagination? The truth is, no one knows for sure. And that uncertainty might be the most powerful answer of all. The parallels are undeniable. Our universe's density, size, and expansion mirror what we'd expect from the interior of a black hole. Time behaves strangely, horizons define our limits, and even cosmic rotation hints at inheritance from something greater. These clues may not prove the theory, but they refuse to be ignored. If the idea is true, then the Big Bang was not the beginning of everything. It was simply the next chapter in a larger story, the birth of a universe within a collapsing star. Our reality would be one link in an endless chain of creations, each universe seeded by the black holes of others. But if it's false, the idea still serves its purpose. It forces us to confront the limits of knowledge. It reminds us that science is not only about what we know, but also about the courage to ask questions we cannot yet answer. Living inside a black hole may sound absurd, but then again, so did the idea of galaxies or black holes themselves not long ago. Philosophically, the question leaves us humbled. If true, it means we are not just tiny within the universe, we are tiny within an infinite sea of universes. Our cosmos is not the whole, but a part of something unimaginably vast. And yet, being part of that chain makes us connected to realities beyond imagination. For some, this idea inspires awe. For others, it sparks fear. But both reactions reveal the same truth. The universe, whether inside a black hole or not, remains far stranger than we dare to think. And in that strangeness lies the beauty of curiosity. What if one day science finds evidence strong enough to tilt the balance toward certainty? What if we discover that our entire existence is nested inside something larger, just as cells live within our bodies? Would that make us feel insignificant, or more connected to the grand design of reality? Until then, we live with mystery. The universe may be infinite, or it may be the interior of a single black hole. We may be unique, or one of countless universes born in a cosmic cycle. We don't have the answers, but we do have the questions, and sometimes that's enough to keep wonder alive. So the next time you look up at the night sky, remember, those stars, those galaxies, that vastness, it might all be inside a black hole. And if it is, then what lies beyond our horizon is not just space we can't see. It is another reality entirely. And that, perhaps, is the most mind-bending idea of all. That the end of one world may simply be the beginning of another.